Welcome back everyone, I'm Jordan Giesecke, and this is The Limiting Factor. This is part 17 of the Lithium Mine to Battery Line series to break down and understand what was unveiled at Tesla Battery Day. Today we're going to look at Gigacasting and the Giga Press. We'll start with some background on the Giga Press, move on to the benefits, and then look at the challenges of casting at this scale. Before we begin, a special thanks to my Patreon supporters and YouTube members. This is the support that gives me the freedom to avoid chasing the algorithm and sponsors, and I hope will eventually allow me to do this full time. The links for support are in the description. Back to Gigacasting. As an opening note, and as with the last video, I'm stretching beyond the usual subject matter of the channel, which is batteries, and into vehicle manufacturing. Everything in this video is based on my best effort to absorb, simplify, and translate a topic that has a lot of depth. Let's start with a bit of background. What is a casting machine? It's a machine that injects molten aluminum into a die. A die is a hollow cavity in the shape of the thing you want to manufacture out of solid metal. The die has two halves that are pressed together to form a tight seal. Large casting machines are measured in tons because that's the amount of clamping force required. The larger the chunk of metal you're casting, the larger the clamp force required. Typically, casting machines max out at around 4,000 tons. In the case of the Tesla Gigacastings for the Model Y, around 6,000 tons of clamping force is required. That's equivalent to the weight of about 15 747s. Why is so much pressure required? First, let's look at the forces involved here. Think of the die as a catcher's mitt. In this case, the baseball is an 80-kilogram slug of molten aluminum that's injected into the die at 22 miles per hour. The machine has to be able to do this 365,000 times a year in and year out, with minimal maintenance for decades. This means that besides the massive clamping force, the machine itself weighs just over 400 tons and is the size of a house. That's some serious iron. But what actually determines how much clamping force is required? This comes down to the size and complexity of the die-cast part. Larger and more complex parts require super high pressure to inject the molten aluminum at high speed so that all the thin and complex portions of the part are formed, and the molten aluminum doesn't cool before the injection is complete. That is, a higher injection pressure requires a higher clamping force to contain it. And just to give an indication of the pressures we're talking here, the bottom of the Marianas Trench is about 15,000 psi. The injection pressure of the Gigacasting machine is a minimum of 25,000 psi for the Model Y rear chassis. There's been talk of the Model 2 using a single-piece underbody casting. I could be wrong, but I don't think Tesla would go this route because I see the pack being manufactured separately from the front and rear assemblies. However, if I'm wrong here and they did go with a single-piece casting for the entire Model 2, it would probably require a clamping force of 12,000 tons or more. This is because the Model Y alone will require two 6,000-ton presses for a total of 12,000 tons, and that doesn't include a casting for the battery pack, which will probably be stamped rather than cast. Furthermore, as the part size increases, the machine size required to cast that part increases exponentially. Overall, in my opinion, the odds of a single-piece casting for an entire vehicle are very low with the current technology. There are two companies in the world that make gigacasting machines, Idra Group in Italy and Impress Plus in China. Both companies are owned by LK Machinery in China, and Tesla is purchasing Giga Presses from both subsidiaries. So far, Tesla seems to be the largest customer for these machines, and I've only seen two other machines sold, which are heading to a Korean company that makes parts for 5G base stations. So far, Tesla has two operational machines in Fremont, which are from Idra, three operational machines in Shanghai from Impress Plus, three underway in Austin, and at least two underway in Berlin. According to Idra's general manager, 9 machines will be delivered in 2021, meaning at least 4 more machines are expected to be delivered this year at Austin and Berlin. My guess is that most will be going to Austin because the Model Y production ramp will be quickly followed by a Cybertruck ramp. Given the size and complexity of a Gigapress, I'd be curious to know how many Gigapresses Idra and Impress Plus can produce per year and how difficult it is to increase the production rate. At the moment, it looks like at least 9 per year from Idra alone, which I'm betting Impress Plus can match. As Tesla's growth accelerates, it may need dozens of machines per year in the steep part of the production S-curve. What about output? According to Idra's documentation, the maximum rate for each machine is 1,000 castings per day. Thanks to footage by the Gaben Cow YouTube channel, if we account for yield rate and downtime, the Fremont Gigapresses may be averaging around 500 units per day. This, of course, raises a question. Why are the Fremont presses running slower than Idra suggests? It could be that Tesla is running the machine slower on purpose, or that they're still working on the S-curve of this machine. I'd like to think that after production has been optimized, and after taking into account yield loss and downtime, that Tesla will be able to produce closer to 700 castings per day per machine, which would mean a little over 250,000 castings per year. 250,000 castings per year would support a fully ramped production line like those in Giga Shanghai. But this is pure speculation on my part. There may be some first principles limit for the particular alloy Tesla is using that requires more time between castings. On the flip side, Tesla tends to push machine speed to the point the machine breaks or they start encountering quality issues. Tesla does this to find the limit of the machine or the process. Then they improve the machine or process to hit higher rates. Rinse and repeat. Although Tesla may be able to improve the current 500 castings per day, I'm doubtful they'd ever actually be able to hit Idra's number. This is because there'll always be downtime and some portion of the castings will be defective. Regardless, it looks like for the new lines at Giga Berlin and Austin, each vehicle will require at least one front and one rear casting, which means at least 2 gigapresses will be required for each vehicle. With that said, the number of gigapresses at a location doesn't necessarily indicate the number of different castings. This is because the die on the gigapress machines can be swapped out in a few hours, allowing the machines to make both front and rear castings intermittently. What are the benefits of using a gigapress to make castings versus the conventional stamped body process? The body shop is at the beginning of the vehicle production line, and anything that happens in the body shop has repercussions down the rest of the line. Even if a few pieces are off by a millimeter, it can throw the entire vehicle out of alignment. The front and rear structures of a vehicle are usually made from a patchwork of stamped sheets of metal. Every joint in that patchwork has to be carefully welded and sealed to ensure that the vehicle won't develop leaks in the interior. To make this more difficult, stamped sheets of metal encounter what's called springback, which is exactly what it sounds like. When the sheet is stamped, the metal bounces back just a little. Springback can vary depending on the conditions that the material is stamped in and how consistent the sheet metal is. Springback can be tamed, but it adds one more headache to production. It results in variations in the shape and dimensions of the pieces that make up the vehicle body. Those misshapen pieces make welding or bonding the stamped parts together to form the vehicle body more difficult and erratic. Besides the springback and welding issues associated with stamped bodies, there are also mounting points that need to be positioned precisely. If the mounting points aren't positioned precisely, or if the body is distorted resulting in wonky mounting points, it becomes more difficult to attach and position parts further down the production line. Overall, any issues in the body shop will result in fit and finish issues like squeaks, rattles, leaks, and gaps. The most common fit and finish issue that Tesla gets pulled up for is panel gaps. Panel gaps don't hurt the vehicle, but they're an indicator of craftsmanship and quality. It's as if to say, if the manufacturer cares this much about something that doesn't matter, how much effort do they put into the things that do? It's perceived rather than actual quality. When a solid casting is used to replace the patchwork of stamped metal parts, it has multiple positive impacts. First, it creates a precise and highly consistent platform to build the rest of the vehicle on, which has positive knock-on effects as the vehicle progresses down the assembly line. Second, it creates mounting points that have micrometer precision. The best analogy I can think of to describe the benefit of going from a stamped body to gigacastings would be building tables from scratch rather than building pre-made tables from an IKEA box. If you make a table a day, you could get pretty damned good at dialing in your equipment to make tables from scratch that are extremely precise and have good fit and finish. To do that takes craftsmanship, knowledge of your tools, and trial and error. This is similar to the current stamped body process. Making the IKEA furniture requires none of that. It's basically paint by numbers. Everything is pre-drilled and cut to size, and it's actually difficult to screw things up. After making a few of these tables, you could fly through the process in less than an hour rather than an entire day. In other words, Gigacastings make the vehicle body and subsequent steps on the line more accurate, more idiot-proof, and also reduce the number of quality checks required. Besides consistency and relieving stress for the entire production line, just one Gigacasting saves 79 parts in the rear body and reduces the rear underbody cost by 40%. A lot of this cost reduction is due to the fact that the Gigacastings decimate the number of robots needed in the body shop. The process of welding the body together takes around 1,000 robots. The front and rear underbody that Tesla will replace with Gigacastings require 300 robots each, which means replacing just these two pieces with Gigacastings will cut the number of robots by 600, or about 2/3. This has further knock-on effects in the form of reduced floor space for the entire vehicle production line. IDRA estimates that Giga Presses will reduce the total length of a vehicle production line by 20%. One final point on the benefits of Gigacasting before we move on. It will allow Tesla to ramp manufacturing lines much more quickly, and when the production line does reach steady state, it will allow Tesla to dial in the panel gaps with extreme precision. As to how far Tesla takes this, it's up to them, but it opens up the possibility of Tesla producing vehicles with the best fit and finish of any vehicle manufacturer in the world. Why haven't Gigacastings and Giga Presses been used before? The simple answer is that large underbody castings have been possible for years. A 4,000-ton press can still make quite a substantial casting. Not necessarily the entire rear or front assembly, but large enough to eliminate dozens of parts, reduce cost, and improve fit and finish. But when you have a large and established bureaucracy like an automaker, common sense doesn't always rule. Internal politics and risk aversion drive decision-making. However, there's more to it than that. Tesla isn't just doing large underbody castings. Tesla is doing massive and intricate underbody castings that don't require heat treatment or coatings and also don't warp. Warping is also known as potato chipping. Let's start with the simplest concept and work up from there. Aluminum coatings are used to increase hardness, wear resistance, and corrosion resistance. One way to create this coating is by dipping the aluminum in acid and passing an electric current through the acid bath in a process called anodization. The image on screen shows two aluminum pistons that were exposed to salt spray. The one on the left did not have a coating and it's corroded. The one on the right did have a coating and the surface is free of corrosion. Coatings like this are clearly effective, but they add time and cost to the process. The next challenge is the massive and intricate castings. This is both a material science problem and a computing problem. The computing problem is that when the aluminum is injected into the die, it does so in a fraction of a second. Within that fraction of a second, the material must fill the die with zero gaps, pits, or seams. This problem can be tackled with a high-powered computer and the right modeling software to model the flow and turbulence of the liquid metal as it fills the die in a split second. The output from that process is used to design a die that can consistently produce pristine parts. The materials side of the challenge is inventing an aluminum alloy that's flowable enough to fill the die rapidly and without defects like cold shut. Cold shut happens when the molten aluminum flows into a die from two or more points and cools as it passes over the die surface. When the flows meet, the leading edge of the flows press against each other and form a seam rather than merging to form a solid part. The solution to cold shut is typically ensuring the material is at the right temperature. However, Tesla's alloy may flow in a way that would help with flow-related issues like cold shut. Next is heat treating. Heat treating is typically done with high isostatic pressure or hipping. Hipping is where a metal is exposed to high pressure and temperature for up to 1 to 2 hours. Hipping is done after a part is cast to increase the strength of the metal by decreasing the porosity. The heat softens up the metal, and the pressure collapses the voids in the metal. Due to the high heat and pressure, hipping is expensive and time-consuming. Finally, potato chipping. After a metal is pulled out of the hipping machine, it runs the risk of potato chipping. This can occur due to shrinkage from the collapsed porosity voids or uneven cooling after the part is pulled out of the hipping machine. If the casting doesn't require hipping, the potato chipping is completely avoided. To solve all the problems with coating, flow, heat treating, and potato chipping with one material is a staggering materials science challenge. To me, it seems like the caliber of material science problem that Lockheed Martin encountered when they engineered the SR-71 Blackbird. A gigacasting may not be as sexy as a Blackbird, but it's in the right ballpark because it would have required Tesla pulling their best metallurgists from SpaceX. According to Sandy Monroe, Tesla has developed a new alloy referred to as 386. It's mostly aluminum with a dash of silicon and trace amounts of 11 other elements. It's worth stopping for a moment to appreciate how difficult it would have been to arrive at this exact formula. Each one of these trace elements is doing something, and changing the amount of any one of the elements would affect how the alloy performs during casting. Even more daunting is the art of knowing what elements to put in the alloy in the first place, let alone the quantities. The universe of possible recipes for an alloy is nearly infinite. To invent this alloy, Tesla must have thrown some serious gray matter at the problem and lots of sweat, because it would have taken thousands of iterations. Let's wrap things up. The material a manufacturer uses for a product dictates the limits of that product and how it's manufactured. Alloys are deeply first principles solutions that establish new territory for manufacturing and design. However, metallurgy is heavy-duty stuff. Elon asked a lot from his metallurgists with the 386 alloy, but it appears they delivered. When the 386 alloy is combined with cutting-edge Giga Presses from Idra and Impress Plus, Tesla will be ramping production lines in record times that are shorter, cheaper, and easier to maintain. Furthermore, at the same time, they'll have the opportunity to do all this while maintaining world-beating fit and finish standards. Now that Tesla's adopted the Giga Press and the world knows the general formula for their alloy, I'll be interested to see how long it takes for other manufacturers to follow suit. Legacy automakers are plagued by internal politics and bureaucracy. Even if the pressure from Tesla forces those internal politics to change rather quickly, it'll take several years for them to get to where Tesla is currently. To get to where Tesla is currently, it would require 4 things. First, they would need to redesign their vehicles to use gigacastings. I doubt they would tear out current machines to do this, and it would only be for upcoming EVs that haven't hit the market yet. Second, which is the easiest part, would be to purchase Giga Presses, which is an off-the-shelf purchase. That is, of course, if Idra and Impress Plus can increase their production rate to supply both Tesla and other OEMs. If there's a bottleneck for Giga Press production, Tesla's in a great position to get first dibs because they've served as a flagship for Idra and Impress Plus. Next is the skill set to master the operation of the Giga Press. Multi-million-dollar, several hundred-ton casting equipment isn't plug-and-play. It takes time to learn how to calibrate and operate the machine. Finally, in order for their castings to be cost-competitive with Tesla's, they would need an alloy similar to what Tesla is using. I don't know if other auto OEMs even have this kind of expertise in-house. Tesla would only have access to this kind of expertise through SpaceX. Overall, legacy auto OEMs may not even bother with gigacastings, and if they do, they may leave it for third-party suppliers to provide rather than taking the risk themselves. This is what years of outsourcing does to your company. You no longer have the confidence to engineer the parts you need for your product to compete. In the next video, we'll wrap up the Lithium Mine to Battery Line series. It's been a long road, but I think it's time to put a bow on it. If you enjoyed this video, please consider supporting me on Patreon with the link at the end of the video, or snag something off the merch shelf below. I'm also active on Twitter and Reddit. You can find the details of those in the description, and I look forward to hearing from you. A special thanks to Sten Carlson, Daniel Carlson, and David McKay for your generous support of the channel, my YouTube members, and all the other patrons listed in the credits. I appreciate all of your support, and thanks for tuning in.